Okay, let's go for the next topic. The next topic is going to be the nuclear physics. In this case, we're dealing with the nucleus. And in the nucleus, as we know, we have particles, protons and neutrons. And all these particles are called the nucleons. Protons, positive charges, neutrons, that's charge equals to 0. Also, the sum of these particles is the mass number. So we have the mass number A, right? A is equals to numbers of protons plus the number of neutrons. Correct. Also, we need we use this symbol to represent the element, and right here we have the number of protons, correct? And right here we have the mass number A. For example, we have hydrogen, right? Or helium is gonna be 2 and 4. Correct? Perfect. Now let's go to the atomic mass unit. Atomic mass unit. By the way, we have right here the mass number is equals to Z plus numbers of neutrons. So the atomic mass unit is used at the scale of the atoms, right? For example, how we pick the mass unit, the kilogram. Well, it's an arbitrary number. We take one object with some mass, correct? Then we take that as the unit, and then we compare this unit to the rest of the masses. The same thing happens at this scale. We have the atoms, right? We pick one atom to be the unit, but because the atoms, most of the atoms, right, have isotopes, right? We have to be more specific in this case. So the unit is taken as the atomic mass unit is the isotope of carbon-12, right? The isotope of carbon-12, right? Carbon-12. That's gonna be the unit, right? Atomic mass unit. So in this case, this isotope has exactly 12 atomic mass unit, right? Has exactly 12 atomic mass unit. Correct? Perfect. An isotope is this nucleus or atom with the same number of protons but different number of neutrons. Great. Now let's go to the size of the nucleus. Let's find how we can calculate the size of the nucleus. Let's do it. Okay, size of the nucleus or nuclear size, right? Nuclear, right, size. Okay, perfect. Size. We know that the nucleus is very close to a spherical shape, correct? So we have a volume. So this volume is proportional to the numbers of particles, right? Protons and neutrons inside of the nucleus. If we increase the numbers of nucleons, right, we increase the volume. But also because this is a spherical shape, the volume is proportional to radius cubed. Correct? From here we can deduce that radius cubed is proportional to the number of nucleons of the mass number A. Correct? Also, we can say that this radius is proportional to 1/3 this mass number. Correct? Let's eliminate this symbol using a constant. So what do we have? This radius equals to this constant times A to the 1/3. In this case, our knot is equals to 1.2 times 10 to the minus 15 meters. Correct? So we have this formula that help us right, to work with the size of the nucleus. This is 1/3, where this quantity 1.2 times 10 to the negative 15 meters. Correct? Perfect. Okay, now for example, let's calculate the density of the nucleus. Let's find that density of the nucleus is equals to gonna be the numbers of particles in the nucleus, which is protons and neutrons, right, times the atomic mass unit divided by, how do we define density? Okay, density, the volume density is mass divided by volume. But what is this mass? Well, is the numbers of neutrons and protons times the unit, the atomic mass unit, correct? Perfect. Divided by the volume. But what is the volume? The volume is 4/3, right, pi r cubed, correct? But what is r cubed? Using this condition right here, it's gonna be A, right, atomic mass units divided by 4/3 pi of r naught, correct, cubed, times A. And what is this? This is equals to A is cancelled from here, correct? And then what do we have? This is equals to atomic mass units divided by 4/3 pi r naught cubed. When we substitute the value of the density of the nucleus is about 2.3 times 10 to the 17 kilograms per cubic meter, to have an idea of the density of the nucleus. Correct? Perfect. Now let's go to, again, analyze the nucleus. What do we have in the nucleus? Well, we have mainly protons, correct, and neutron. If this is a proton, this is another proton, for example, well, these charges repel because they have the same polarity, the same sign, right? These two repel. Means that must be a force that keep these two protons together, right, in the nucleus, right? And this force is called the strong nuclear force. Now let's go to the strong nuclear force. Correct? Perfect. And this force, for example, is an attractive force. This is, right, it is an attractive force. This force is a very short range force, right? It is a very short range force. It's about 10 to the negative 15 meters, correct? It doesn't act on electrons, only on protons, correct? And it's stronger than the electrostatic force, right? It is stronger than electrostatic force. We can calculate the electrostatic force. Remember, using the electrostatic force, the electric potential or potential energy of these two protons, right, is equals to K, right, this quantity plus this quantity divided by the distance, or the distance r is about, as you can see, this quantity. So let's do it. Let's calculate. It's equals to about 9 times 10 to the 9, right, newtons meters squared divided by coulombs squared times what? 1.6 times 10 to the negative 19 coulombs squared divided by 1 times 10 to the negative 15 meters. Right? So when we do this calculation, we'll see that this energy is about 2 times 10 to the negative 13 joules, or equals to, you said electron volts, about 1 times 10 to the 6 mega electron volts in this case. electron volts, yes, electron volts. So again, the force acting on the nucleus must be more than this electrostatic force. Correct? Perfect. Now let's go to, instead of using forces, also we can use energy, like in this case, right? Potential energy, when we have two charges as the potential energy. Well, let's go and use the same term for studying the nucleus. Correct? And we call this, instead of the forces, we call this the binding energy, which is similar to this energy right here, right? Binding energy. And let's define this binding energy. Okay. The binding energy is the energy that would be needed. Let me write it down. Right? Is the energy that would be needed to disassemble a nucleus, correct, a nucleus into individual particles, into individual nucleons or particles, nucleons. Right, that's the binding energy. Right, that's the energy. We can say that the energy that keep these protons, right, nucleons together, or in the same way we can say that is the energy that would be needed to disassemble, right, this nucleus into individual nucleons, protons and neutrons, right? Okay, so also it's found that when we have these particles free, right, neutrons and protons, imagine that this is the mass, right, mass of these particles, protons, right, and neutrons, and we compare this mass to the mass inside of the nucleus, right, with the same number, right, of particles. Well, if we call this mass of the nucleus, for example, it's found that this mass is greater than this mass. And the difference is called the mass defect. So n of the particles are free, separated, right, or disassembled, minus the mass of the particles in the nucleus is equals to this mass defect. Right, delta M is equals to mass defect. Let's call the mass defect. Correct. Perfect. Now we can define the binding energy in function of this mass defect. In this case, we use one of the most famous, or actually the most famous equation in physics, which is energy is equals to mass times c squared. Correct. In this case, we're dealing with rest energy is equals to mass times c squared. Correct. And then what do we have? Binding energy. Let's represent the binding energy by B. Right. So the binding energy is equals to the product of the mass difference, right? Mass or mass defect times c squared. Remember, c is the speed of light in vacuum. Okay, and we can define again the binding energy in this way. Perfect. Or also, let's go to the definition. And we have in this case that if there is energy, because energy needed, right, to disassemble the nucleus. Imagine this is energy, and we have right here the nucleus, right, the nucleons right here, right. And then what do we have? Well, we have that these nucleons are disassembled, right? We have the separation of the nucleons. So what do we have? This is the binding energy. So gonna be energy, correct, plus the nucleus, right? Nucleus must be equals to this disassembled nucleus, right? Disassembled nucleus. Okay, now let's give some symbols. It's gonna be the binding energy plus, again, let's go to using the rest energy, right? So equals to, again, mass of the nucleus times c squared is equals to numbers of protons times mass of the protons plus numbers of neutrons and mass of the neutrons, correct, which is right in the nucleus times c squared. Correct. Okay, perfect. Now let's solve for binding energy. So binding energy is equals to, one more time, numbers of protons times the mass for each proton plus numbers of neutrons, the mass for each neutron, minus now the mass of the nucleus, correct, times c squared. Correct. Perfect. Now, instead of dealing only with the nucleus, mass of the nucleus, it's better to work or deal with the mass of the atom. In this case, we need to involve or include the mass of the electrons. Okay, let's do that. Let's include the mass of the electrons to get a general equation for the binding energy. Let's do it. The mass of the atom, remember the mass that we have on the periodic table is the mass of the atoms, including the mass of the nucleus and the mass of the mass of the nucleus and the mass of the electrons. Correct? That's the mass of the atom, right? Atomic mass. What is gonna be equals to mass of the atom, right? And this is equals to what can we do right here? Mass of the atom is equals to mass of the nucleus plus this is mass of the nucleus, correct, plus z times the mass of each electron. Correct. Now let's use this in the previous formula. Remember the previous formula, we have that the binding energy is equals to z mass of the proton plus n mass of the neutron minus, right, mass of the nucleus times c squared. Okay, now let's involve this quantity, correct? And in this case, we add and subtract that quantity. Let's do it this way. Look, it's gonna be B is equals to, one more time, C M mass of the protons plus, now let's add Z mass of the electron, and they've got to subtract it too, right? What else? Plus numbers of proton mass of, numbers of neutron mass of the neutron, correct? Minus mass of the nucleus, minus, because we added this quantity, which is right here, we have to subtract it to keep the same quantity as before. Perfect. Minus what? Z and E times C squared. Correct? Perfect. And what is this? This is a Z times mass proton plus mass electron, correct? Plus numbers of neutrons, mass of neutrons, minus, now it's gonna be the mass of the atom, right? The mass of the atom times C squared. What is this? This is the mass of hydrogen. M mass of the proton plus mass of the electron is equals to mass of hydrogen. From here, what do we have? We can have that the binding energy is equals to Z time, this is the atomic number, right? Z, atomic number or number of protons in the nucleus, times mass of the hydrogen atom, plus n numbers of neutrons, mass of the nucleus, minus the mass of the atom times C squared. Correct? Perfect. Now, it's better if we involve the atomic mass unit in this formula. Remember, how do we define the atomic mass unit? Well, it's equals to, using definition again, we know that is taking the isotope of carbon-12 to be right with 12 atomic mass units. And using, sorry, here, it's not here, okay. Using kilograms, this is equals to 1.6605 times 10 to the negative 27 kilograms. Okay, now let's see the energy that is equivalent to converting this atomic mass unit into energy, right? So what do we have? Let's use this formula, right? The rest energy is equals to mass times speed of light squared. In this case, we use atomic mass units as the mass, right? Times C squared. What is this? This is equals to 1.66 times 10 to the 27 kilograms times 3 times 10 to the 8 meters per second squared. When we do this calculation, it's found that it's equals to 1.4924 times 10 to the negative 10 joules. Also, we convert this into electron volts. It's equals to 931.5 mega electron volts. Correct. So what do we have? We have the energy is equals to 931.5 mega electron volt. But also, this is equals to what? This is equals to, look, mass times energy. But what is that mass? Atomic mass units times mass times speed of light square. So it's gonna be to that quantity. Now let's work with this part, and we're going to solve for C squared. So C squared is equals to 931.5 mega electron volts, correct, per atomic mass unit. So we substitute this value right here, and what do we have? We have that the binding energy is equals to Z, mass of a hydrogen, plus numbers of neutrons, mass of each neutron, minus mass of the atom, correct, times, now let's add this quantity times the mass of the atom, correct, times 931.5 mega electron volts per atomic mass unit. And this is the formula that we use in most of the cases for binding energy. Because it's easier, it's better when we work with atomic mass unit. So atomic mass unit is cancelled, right? Because it's divided by that quantity, and we make calculation faster, easier in this way. Got it? Okay, perfect. And with this, we finish this part for nuclear physics. And the next video, we're going for the second part. Okay? Thank you, and see you in the next video. Bye.